Hey, let's get started. So today we're very pleased to have Professor Ben Shappee to give us the Astro Colloquium. So Ben got his PhD from the Ohio State University in 2014. After that, he spent 3 years at the Carnegie Observatories as a prestigious Hubble Carnegie Princeton Fellow before he joined the astronomy faculty at the University of Hawaii in 2017. Professor Shappee is a world-leading expert on optical time domain surveys. He is one of the founding members of the ASAS-SN survey to explore the dynamic bright sky. And he was part of the small team that discovered the optical counterpart of a gravitational wave event from a neutron star merger back in 2017 to officially kick off the era of gravitational wave and EM joint observations. And he has worked on a broad range of astrophysics from exploding stars to monster black holes in AGN. And today he will talk about the ASAS-SN survey and its impact on time domain astrophysics. So Ben, please take it away.
Awesome, thank you. So this talk, thank you for the great introduction. This talk is broken into basically two parts. The first part, I'm going to kind of quickly go over the landscape of the bright transient surveys, the major ones, to give kind of everyone on the same page when they to put ASAS-SN into context with the other surveys that are around. And then maybe the last 2/3 of the talk are broken into a bunch of different sections where I go through and I will give one of the new opportunities that are in transit astronomy right now, and then give one example of that. And I know I'm zoomed out, I'm sure other people are. If you kind of lose track of one part, don't worry, you can jump in the next part, or please interrupt me, ask questions. I usually do better when I'm asked questions. If there's lots of questions, I can just cut off things at the end, so it's pretty easy. So thank you for this opportunity to talk to you. I first want to mention kind of the group I have in Hawaii that I formed on the top of this slide. Those are my grad students currently here. Most of them are Astro, but Kyle Hart is actually a computer science graduate student. The bottom left are my two REUs from last year. I'm the co-director of the IFA's REU program. So these are the two I did last year. I'm not going to mention actually their work in this talk, but they're both extremely good. Both have papers about to come out. So if you see their applications, I encourage you to take a very close in-depth look at them. And on the bottom right are the two postdocs that I just hired recently to work on different things. And so I'm going to use basically most of my students or postdocs' work to highlight different aspects. So then I'll attempt to show, I think I do it most of the time, I show a picture of them when I'm talking about their work. So the first thing when you think about transient surveys is that you kind of think that, well, if you're not in transit astronomy, you might think that we have tons of surveys. We must be doing the entire sky all the time. And that is true now, but actually ASAS-SN is the first survey to do both the northern and the southern hemispheres in real time when we deployed our Chilean unit in 2014. And this is now expanding. Well, here I show you basically the major surveys, which these are for bright sky. So obviously I'm including things like DECCAM or like Subaru Hyperstream Cam. And the black ones are the ones that currently exist, and the grays are the ones that are currently being developed or deployed. This should be this upcoming year. So what you see is that most of the surveys are in the northern hemisphere, and then they're also in relatively one region, basically either Hawaii or California when it comes to their location, and so they're relatively close in longitude. This has become important because when you combine these surveys, we're starting to get to a point in transit astronomy where we have more than 1 day cadence, at least for the bright sky, over the entire sky. So then you want to start to spread out both in hemispheres, but also in longitude, so that you can start to actually take advantage of that sub-day cadence by having multiple different sites. And it's kind of a puzzle work, but this is kind of the basic layout where ASAS-SN really is the bright sky. That's what we were designed to do. So we just make sure that basically nothing falls through the crack that's bright. And we cover basically the entire visible sky every 20 hours. You go a magnitude deeper, you go to ATLAS, which is primarily an asteroid survey, although it is branching out. I'll talk a little bit more about that in a second. Slower cadence, but about to develop 2 more units in the southern hemisphere, in which case it'll be the second survey to do basically the entire visible sky on a regular basis. ZTF goes about a magnitude deeper than ATLAS. Again, a little slower cadence here. I'm showing you the public survey cadence. Pan-STARRS go substantially deeper than ZTF, about a magnitude and a half. It's kind of the breakover point where I would say we're going from bright transient surveys to fainter ones, but slower. And then TESS is what you might not think, although I know, of course, a number of people here are thinking about TESS as a transient survey, but it had 30-minute full frame images. Now it has 10-minute full frame images, and basically kind of a depth roughly ASAS-SN to ATLAS. It really depends on where you're on the sky you are, and exactly what you want to do. And of course, you can stack, if you don't care about fast time scale, very fast time scale, you can also stack and go deeper. All right, so the combined, this is kind of the state of the field, is that the number of transients we're discovering is exploding with time. So this brings both the opportunities and the challenges I'll discuss later. The field itself is also exploding, pun intended, with both the number of people, number of young scientists in it. The kind of the foreseeable 5 years, maybe 10 years are quite bright for transient astronomy. I'll just break down the number of papers that reference or use data from various surveys as a function of time. And this is papers per year. This is not cumulative. Obviously, PTF goes down because ZTF started. And the ranking on this is not a particular thing I want to highlight necessarily. But one thing I should mention is, of course, that Pan-STARRS would basically be double the height of ASAS-SN. Except here, I'm trying to focus on just transient time domain surveys, so the time domain aspects, and then Pan-STARRS, of course, has huge use for its static sky, so it's difficult to separate those two away. But just to keep in mind, obviously, Pan-STARRS is extremely well cited, has a high impact in the community as well. I'm going to quickly go through, kind of give you an idea of how the different surveys, their details. I'll spend a little bit more time on ASAS-SN. So ASAS-SN has 5 fully robotic units distributed at 4 sites around the world currently. We have one that we're trying to commission in China. Each unit has four 14 centimeter telephoto lenses backed by 2K by 2K thermoelectric cool CCDs. Our pixels are quite large, 8 arc seconds in the sky, although it's much smaller than TESS. Limiting magnitude now, because we switched to G-band, we go a little deeper, it's about 18.5. If you go back in time, we were running D-band on 2 of our units, which only went to about 17.5. But between the 5 units we already have commissioned, we can do more than the entire visible sky every night. Obviously, we can't observe behind the sun. ATLAS specializes in finding near-Earth asteroids, basically things that hit us, or that are going to hit us or might hit us within a couple of days warning. That's what its mandate is. But that same capability also makes it extremely useful for transient astronomy. They have these new 10K by 10K CCDs, beautiful chips, very wide field of view, very nice. 2 half-meter telescopes, also very nice telescopes on Mauna Loa and Haleakala, and they're deploying 2 more this unit in the year in the Southern Hemisphere in Chile and in South Africa. The pixel scale is about 2.5 arc seconds per pixel. ZTF is using the old 40-inch telescope. It's finally plastered the focal plane with these 6K by 6K very nice chips. So they take full use of their full field of view where PTF was not. This is I think this is the same as for the new MSEP, I'm not actually sure, but this is for the old MSEP. 40% of the time is actually public survey. 1 arc second per pixel. So they go about magnitude deeper than ATLAS. But of course, they're a single site survey. So weather gaps, especially because we're now getting to the time scale where we're sub-daily cadence and weather is correlated on more than 1 day cadence, being a single site is a disadvantage when it comes to weather, and as is how the transient kind of field is going. Pan-STARRS is also a single site, except now it has 2 telescopes. Everything you think of Pan-STARRS is done with PS1. PS2 is I've been told, finally getting towards the end of commissioning. Both the cameras are still the world's largest cameras in the world. They will be supplanted, of course, by LSST when it comes online, or the Rubin Observatory. It goes substantially deeper than ZTF, but substantially slower. It's at a better site, of course. Haleakala is a much better site than Palomar, typically speaking. Scene's usually better, so they can take advantage of their much smaller pixels often. Yeah. The last one that you might not think of, if you're not a transient astronomer, or even some transient astronomers, wouldn't quite think of TESS, but the full frame images are quite useful. The full missions, the main mission is now done. 2 years of data, has these 4 cameras that kind of step through. You can kind of think of it like an ASAS-SN unit in space, except the lenses are smaller and the PSF is actually, and the pixels are substantially larger. But the photometric precision can be exquisite. We're currently in the middle of the first year of the extended mission, where it's redoing the southern hemisphere, and then it'll do most of the northern hemisphere again, and then some of the ecliptic that I missed right here. So really what I'm trying to have the community saying is that TESS isn't just a Transiting Exoplanet Survey Satellite, but I want them to also think of TESS as a Transient Explorer Survey Satellite as well. When you think of TESS, why am I so interested in TESS? There's a couple of reasons, but I think most of them can be summed up on this plot, which is that this is a common plot in transient astronomy. The original plot is often credited to MAXI, where you can plot different types of transients on a space of basically characteristic timescale. So that's the characteristic timescale of the transient. 1 day is right here, and then it's peak luminosity. Right, so you have thermal type 1A supernovae, you have core collapse, you have the kilonova that was just mentioned, you have GRBs up here, right, because they're beamed, they're relativistically beamed, they can have much shorter time scale. Then if you plot, then to plot a survey over this diagram, what you have to do is get a distance. So if you go out to the distance of coma, TESS looks something like this, where this is 30 minutes, so it's taking 3 of the 10-minute exposures, and so you have 3 detectors on the transient that's at this time scale. Then as you can stack more exposures to go to longer time scales, you can go deeper and deeper. And you see that you catch a lot of interesting transients, but as you go closer, this can be a theme of this talk, nearby bright transients have intrinsic interest because you can study them easier and you can get them more readily. But as you go closer to Virgo or Andromeda, then you get a large amount more range in this diagram. And what's particularly, 2 things that are interesting with TESS. One is that this left region of the diagram, which is mostly unexplored or explored only in certain situations, I would not say a thorough systematic search. So this is finding new transients that would be missed by ground-based surveys in the TESS data. Some folks are doing that. What I've been focusing more myself on is looking at kind of transients that are discovered from ground-based surveys, but using the exquisite photometric precision and time scale and time resolution of TESS to kind of explore them in exquisite detail, especially at the early time. So you can both the left and the right hand side of this plot. TESS is an interesting for transient science. Okay, so this is a diagram that was put out by ZTF, basically comparing the field of view of different surveys. ZTF is shown here, Pan-STARRS, LSST. You can see IPTF's upgrade to ZTF, and then DECAM, etc. And one thing to realize with this plot, and this is true in this plot right now, is that these have very vastly different depths. Like LSST is obviously much deeper than ZTF, etc. But they're just comparing field of view, which is one direction to compare transient surveys. So if we add the second Pan-STARRS unit, right, it kind of looks like something like this. A single Atlas unit looks like this, but there's currently 2. So I'm kind of completing this diagram with the other surveys that I've talked about. ASAS-SN, a single unit, is a little bit smaller a field of view than an Atlas unit, but we have 20 of them. And then, of course, I just told you Atlas and ASAS-SN are both expanding. So if you add them as well, it looks more like this. And then finally, if you add TESS to, interesting. Don't send. If you add TESS to that diagram, then obviously it'll be much larger. So it's already reloaded. Let's see if this works. Can everyone still see the slide?
Yep.
All right, perfect. And of course, these are different depths. So I'm not saying that this is equivalent. You shouldn't use this one dimension to compare things. The point I'm trying to make is that each of these surveys that I've mentioned so far have a different region of parameter space that they specialize in, and each region is important. So if you want to do just total confirmed supernovae in 2019, it's shown here. TNS, Transient Name Server, changed their script. Otherwise, I would have updated this for you guys. Sorry, it's still running for 2020. But this is what it looked like in 2019. ZTF has the largest by number, but again, a theme of my talk is that brighter objects, I would argue, intrinsically have more interest. Although obviously, if you have a larger number, then you can find rarer objects. But if you look at just the bright ones, this is what it looked like in 2018. So you see that ZTF, Atlas, and ASAS-SN were all about the same when it comes to discovering bright nearby supernovae. What's interesting is if you go back in time, and that'll come up a little bit more in this talk. So if you go back to 2018, it looked kind of like this, where ASAS-SN was the dominant discoverer. Atlas was starting to come in. But an important thing to note is that the amateurs were still the third leading discoverer of nearby supernovae, bright supernovae on the sky. These are the easiest ones to find. There's a number of amateurs. They're extremely talented. They're very good. And so they were contributing a lot. If you go back to 2017, roughly the same. 2016, amateurs are actually number 2 because Atlas hadn't really kind of taken off yet. 15 and 14. And what you can see is that the ratio between ASAS-SN and amateurs favors the amateurs more and more as you go back in time. And actually, before we went real time in 2014, May of 2014, the amateurs were actually the dominant discoverers of nearby supernovae. So all of the samples for the nearby bright supernovae that was discovered before 2019 are particularly biased because it's hard to understand exactly what the amateurs were deciding to look at when they wanted to find supernovae. Okay, so that was quite quick, but I want to ask if there's any questions about kind of surveys, different places of surveys before I jump into the second part of my talk, which is kind of talking about the opportunities and challenges that face kind of the transit community right now.
Well, maybe just a very quick one, Ben. So the amateurs, they discover a lot of the bright nearby supernovae, but I'm guessing that a lot of the supernovae are also independently discovered by ASAS-SN.
Yeah, so that's a great point. I should have clarified. These are discoveries. This is a point of contention. Well, anyway, this is an interesting point in the community right now. Like, what does it mean to discover? Here, I will always use discovery to mean the first to see something and publish it. So there are lots of recoveries, but all these are independent. So one supernova only goes into one bin here. And so, yeah, especially once ASAS-SN started, those would have been recovered. But before ASAS-SN started, it's hard for me to actually say that. That's a good point.
Yeah, thank you for the great summary. So I was wondering if you could remind us about the expected population, perhaps missing from the bright and really fast transients in the parameter space of the the luminosity versus the time scale. So is there a large population of undiscovered transients at all?
That's a good question. So basically you're asking, basically in this region of the diagram, there are certainly, we've started to discover some of them, like bright transients. They're usually called like F-bots. Well, some of them are, if they're blue, fast blue optical transients. We know that they exist. They're particularly hard to find in our current surveys because they drop quite quickly, although we're just now getting to the point where we'll start to recover more and more of them. And the number or the fraction of them will really depend on what their luminosity function is, because it's going to be particularly difficult to discover things that fade fast and are intrinsically faint because you're not probing that much of a volume. So to get complete, so basically if you want to be complete in something, right, you have to have a survey capability that goes substantially below and to the left in this plot to really like be complete for a sample. So right now, most of the surveys, I would argue, are kind of not going to be complete at all, but we're going to start to find a much larger fraction, a number of them, and we are starting to right now. It's a great question.
Okay, thank you.
Hey, Ben. So these are all photometric surveys, and the plot you're showing right now is V-band. Could you just say just very briefly about what the filter situation is among all these different surveys?
It's a great question. I don't have a good slide for this. I should. That's a good point. Now let's go here for now. See if this works. Yeah, so these are all obviously optical surveys. I think there's a lot of interest in the community to start to go to bluer filters and redder filters to go into the optic, like near the UV if we're going space, actual UV or the IR. But ASAS-SN is G, so we're somewhat blue. Atlas has a very unique filter set. One is orange, where they do most of their observations, unless when the moon is bright, in which they switch to cyan. Orange is R plus I, cyan is G plus R. So the broader filters, so they can go deeper at the cost of having non-standard filters, which causes lots of headaches, which I won't go into. I use a lot of Atlas data. It's a great survey. ZTF is G and R. And Pan-STARRS is now most of the surveys in W, so white, so it's just open, because Pan-STARRS is now completely paid for by NASA for hazard assessment. Oh, yeah.
Cool.
Thanks.
Thanks.
And then TESS is redder. It's kind of like it's redder than even Kepler was. So it's kind of like R plus I.
Great. Thanks.
Absolutely. Any other questions before I move on?
So just to clarify, when you're reporting the Pan-STARRS numbers, is it only the part that's actually discovered in W by the asteroid survey?
Yes, I'm not using like YESI or YSE or any of that.
Yep. Sounds good.
Yep, that's true. Pan-STARRS obviously has more filters, but when I'm talking about W, I mean just what they're using the majority of their time doing searching the sky. That's a good point. Awesome. Okay, so I'm going to break opportunities and challenges into a number of different kind of regimes. These are kind of when I think of like usually when I think of what projects to lead or have my students lead, I try to think about where there's unfair advantages and where we could, where there's new opportunities that weren't there before, because those are usually the areas where you can make the most progress with the least amount of effort, and I'm intrinsically lazy. So so this is the way I kind of think of things. I'm sure there's more, and I'm going to focus. I just want to mention again, I'm going to focus on just kind of examples of science in each one of these categories, mostly focusing on what my own group has done. But obviously, there are tons of examples in each one of these. So less biased transient samples. And if you go back in ASAS-SN, so I just mentioned that the amateurs were discovering a decent number of supernovae. So this is looking at a sample of supernovae discovered between 2014 and 2018. And it's broken down by who discovered them. This is work done by Tom Horloin in 2018. Red is ASAS-SN, blue are all other professional surveys combined, and black are amateurs. And on this parameter space, what I'm showing you is the offset from the center of their host galaxy in physical units, kiloparsecs. On the x-axis, I'm showing you a proxy of how large the galaxy is. So it's the K-band absolute magnitude. So large galaxies on the right, small galaxies on the left. The dashed vertical and horizontal lines are the medians in each one of those structures for the three different samples. So there's two things that I want you to see here. The first one is that ASAS-SN and professional surveys on this sample are both the median is substantially smaller galaxy than the amateurs. And that's because the amateurs are extremely smart people. They have limited telescope resources. They have not huge field of views. And if you want to maximize the number of supernovae that you want to discover, you want to look where stellar mass is, because supernovae track stellar mass to 0th order. And so they look at larger galaxies in the nearby universe. They don't like spend their time looking at very small galaxies. Okay, so that makes sense. And it's a large effect. It's about an order of magnitude. But what's more surprising is the y-axis. If you look at the y-axis in this sample, the amateurs, find supernovae that are farther out. It makes sense. A lot of them aren't subtracting. They're just like visually looking by eye. They're, again, very talented. I cannot do that work. Patience for it. But they're looking at the images by eye and kind of like identifying new sources that way. But I think what's the most surprising part is that between the other professional surveys and ASAS-SN finds supernovae that were about a factor of 2 closer into the center of their host galaxies than the other professional surveys. This is surprising at first because our pixels are larger than all other professional surveys. But then if you think about it, since most galaxies in our volume are point sources to ASAS-SN anyway, we don't actually care if they go off in the center or closer to the outskirts in the host galaxy, because it's all the same to us. If we can't subtract the host galaxy, we're not going to find it anyway. It doesn't actually matter that much where in the host galaxies it goes off, except for the very closest ones. You also change the y-axis into arc seconds, and the same thing persists. It's not just that ASAS-SN is finding closer supernovae than the other professional surveys in the sample. This effect is starting to go away with ZTF and with Atlas, but that's just another advantage. So we should redo some of these analyses. Why is this interesting? Well, if you actually want to know where supernovae go off in the local universe, you have to see them go off in the local universe and then correct for that. And you can't correct for it if you don't even see them in the first place. So if you look at like LOSS sample, which was a galaxy targeted supernova survey, which did a lot of this early work, you have it in blue right here. You can see that they just don't, the cumulative distribution, they just don't have supernovae going off in small galaxies because it's not looking there. PTF was a sky survey, an all sky survey, not a galaxy targeted survey. So I found them in smaller galaxies, but the previous thing I just showed you, so that ASAS-SN was more complete, you can actually see that in the cumulative distribution as well. Basically, ASAS-SN has a larger number in the small galaxies. And this is interesting because then you can, for 1As, you can then translate that into relative specific supernova rate. So this is the number of supernovae going off per unit stellar mass in a galaxy. Blue is what was seen by LOSS, where as you go into smaller galaxies, you had more and more supernovae, not just, more and more supernovae per unit stellar mass. But then as what we see in ASAS-SN is because we have all these small galaxies, you can see and measure that this trend continues to much smaller galaxies. So you have almost a 2 orders of magnitude dynamic range in the specific supernova rate for a supernovae. And this isn't just important to understand what the progenitors are, but it's also important if you don't care about supernovae at all, but you care about galaxies and metal enrichment and galaxy evolution, because the galaxy survey or galaxy models and evolution codes aren't taking into account the fact that there's such a strong function in the 1A rate. And so, I know there's a number of groups now that are starting to use these results and then go back into galaxy evolution simulations and actually put in a more physically motivated supernova rate.
Hey Ben, just a quick question here.
Yep.
Clarification. So this is a number of type 1A supernovae per decade in stellar mass. So, but for smaller stellar mass, we also have more galaxies, absolute number of galaxies, right?
Yeah. So
this is not the number per galaxy.
The relative specific supernova rate is the number of supernovae per unit stellar mass that's there.
Right, but not per galaxy.
It is per. Yeah, it's not number per galaxy. So
right.
If you asked, so there's not. If you took a small galaxy, took a big galaxy, it's not that there's more supernovae going off there.
Right.
Which is much more than you would think there was given its stellar mass. That's a good point.
Mm-hmm.
And if you asked where most supernovae go off in the local universe, you didn't have to hit this with a mass function of galaxies. And the answer is not that they go off in the small galaxies. They still mostly go off in like Milky Way-ish galaxies in the local universe. So if you want to know, if you want to ask the question, where do most 1As go off? That's a different question. This is related, but not directly answering the question. That's a good clarification point.
Okay.
And so just real quick, does this also account for the potential population of obscured population, if you consider, like the smaller galaxies are potentially more dusty?
That's a great point. This does not do any post-galaxy property corrections. So if you, that's a much more difficult thing to do. You probably have to go to like an IR survey, and we're just starting to get to those points now where you can really start to look for obscured galaxy or supernovae and measure their rates by IR transient surveys. But yeah, this does not try to make any corrections for obscuration. It's more of a problem in type 2s than it is in type 1As, but it still is a problem in type 1As.
Okay, thanks.
Sorry, one last question. This is a provocative plot. So is this, the trend is quite impressive. Is this a reflection of there's more star formation in the smaller galaxies, or is this a delay time issue? What's supposed to create that trend?
So that we didn't speculate that in the paper itself. I would argue it's not completely clear which one of those it is, but yes, it's one or both of those. I think it's probably both. I think it's dwarf galaxies produce more stars per unit stellar mass, of course. That's known for a long time. and the delay time distribution for 1As, right, it goes something like t to the -1. So a
Right.
large number of your supernovae go off really quickly, even
Yeah,
for
yeah.
1As, not just
Right,
close up. So I think it's a combination of those two effects. Is there an additional effect on top of that, like the populations themselves are fundamentally different? I'm not sure of that. I think that would take more careful work, but I think that's an interesting question to start to investigate. Basically, like, can you explain it all away with just those two facts? Or maybe the supernovae themselves are different in those populations. There's hints from, we could do entire, like, anyway, I have an entire colloquium that's on just 1As. But you can imagine that the progenitor systems themselves are different. There's metallicity correlation with binary separations that's been shown in the past, like, 1 or 2 years now, where there's more tight binaries in lower metallicity environments.
Mm-hmm.
Maybe that has something to do with it. So anyway, I think the answer to your question is yes, and maybe something else.
Cool. Very nice.
Okay, I'm gonna have to trim something. Anyway, you guys seem to like the 1A, so I'll continue on here. So another thing, right? You can do for large a large sample of transients. Right, so we get a large population of normal transients. You don't have to. Everyone has to be special. And one of the real things that when you think of 1As, right, you think of using them as cosmological tools. And that is true. The cosmological parameters are being pretty pinned down, especially by 1As now. There's still some uncertainty there. Systematic errors given what their progenitor systems are. But since coming to Hawaii, I've started to talk a lot with Brent Tully, who uses them, wants to use them in a very different way. Basically, what we want to do is cosmography, which is, I think, a current term that he coined. I'm not actually sure who coined that one. But basically, it's mapping out our local universe. So you think that, at least when I took cosmology, we're like, there's a cosmologically uniform volume, right? If you go out to large enough scales. The thing is that we're not actually there yet. So we've only actually looked at large scale structures out to a redshift of about 0.05, because that's what's being shown here. 0.05 is like 15,000 kilometers per second. And that's because to do this work, mostly what's been done is using galaxy correlations, like Tully-Fisher relationship, for example. But the intrinsic dispersion there is 30%. And to do this work, where you actually want to map things out, you need both, obviously, RA and deck, the position, you need its distance, and you need a redshift to get peculiar velocities. And then you can, when you have a bunch of points, you can use them as test particles to basically map out where they're going, and then use that to map out the large scale structures that are gravitationally bound. So here, this is work from that made a splash in 2014, where they use these relationships to find that Laniakea is a supercluster, which is what we're part of. Laniakea is a Hawaiian word. There's a whole effort in Hawaii now to name astronomical discoveries and give them indigenous names to kind of connect back. But so you see these large structures, and this is only in 2014 that we discovered that we're actually part of this thing. So the idea here is that if you want to go up farther than a redshift of 0.05 and try to get to where the cosmological uniform volume is, you need more precise distance indicators to do that. Okay, so what's more precise? Well, supernovae can be substantially more, or are more precise distance indicators than galaxy correlations are. But then you need a large number of them. If we want to go out another factor of 2 in redshift, it's almost an order of magnitude in volume. And so what we're doing, we've started this, one of my students, Aaron Doe, and I just hired a postdoc, Thomas de Jager. We're going through and we're trying to build a sample eventually of 10,000 supernovae discovered by the transient surveys I just mentioned. They give you optical light curves for free, because they're already doing that anyway. Then we can trigger a UCURT, which now University of Hawaii owns and operates, to get an IR light curve, at least a couple points, because the scatter in the IR is substantially less, and the number of supernovae you need scales very strongly, right, with the scatter, because more precise test particles, when you're trying to find these gravitationally bound structures, obviously the more precise, the less particles you need to average out over. So getting the IR helps us a lot there. But then you also need the host galaxy redshift. A decent fraction of that we're doing with the 88-inch, and the other fraction we're going to rely on spectroscopic galaxy surveys, either ones that have been done in the past or kind of hopefully going forward with other current galaxy surveys. Okay, then Okay, we have light curves from transient surveys, UCURT. We can fit those supernovae, get distances. That's what 1As are good for. We have the redshift from the host galaxy. Then you can do a Hubble diagram. And what you do is you play the game where you fit the Hubble diagram, but you're not looking for H0 here. You're looking for deviations from H0 that are correlated on the sky with their positions. So then you get the peculiar velocities, and then there's a variety of different techniques to filter those peculiar velocities, if you have a good enough sampling, in to actually look at these structures. And so we're basically trying to map out the nearby universe out to a redshift of about 0.1. And this was called the end of greatness by Bob Kirshner at one point. Basically, and the idea of this project is to actually understand kind of our local neighborhood on the largest scale that you can really call kind of our home. Any questions here before I move on? If not, we're going to go on to bright examples for in-depth study. So I said multiple times already that brighter transients are typically intrinsically more useful. Depends on what your case is, but if you want to study them, then if you want to use them to study the physics of the transient itself, because you can get a lot more data on those sources easier, and you can just see them earlier. So we started talking about 1As a decent amount already. You can broadly break down the progenitors of type 1As into two different categories, whether they be single degenerate or double degenerate, where single degenerate is you have a white dwarf, carbon oxygen white dwarf accreting from a nearby companion, main sequence star, subgiant, red giant, until it gets close to Chandrasekhar mass, starts simmering in its core, and then eventually ignites the carbon and oxygen and explodes as a 1A. This is historically what was thought to be more, historically the last 40 years, to be the more likely channel, although now it seems more like it's double degenerates, where you have two white dwarfs that merge or collide to explode. There's huge numbers of variations in the different models, but these are kind of the two main classes. And there's even difference between how they explode and what the progenitor system actually is. But to probe this, the fundamental thing here is that you have a nearby companion, so you can look for interactions between the ejecta and that companion to try to infer the existence of a nearby companion, or you can, if you don't infer the existence, then you can assume that it's double degenerate because there's no observational evidence. So what is one of the ways that you can look for the interaction between the ejecta and the companion? Well, as the ejecta comes out, it's going to strike the companion, heat the surface, and you can see a hydrodynamic simulation here on the right-hand side. Hit the companion, creates a shock. You have a bow shock. Shock goes into the companion, and then materials removed from the companion, both by stripping, which is just momentum transfer. So if I punch my coffee mug off the table, but actually the predominant source is actually the shock that goes into the companion, overheats it, and then after the ejector goes by, that material just ablates away. Basically, just is too hot. But hydrodynamic simulations have robustly showed that for a main sequence star, you expect about a tenth of a solar mass to be removed. And the lower the surface gravity, the larger the star, because it's rotational overflowing, then the more material you typically expect to be removed. This is work that I did a long time ago on 11FE, which was a particularly good one. The nearest supernovae since the brightest supernovae since 1972E. So we can place really good limits. This game's hard to play if you want to actually look for that material that's stripped, because that material that's stripped is at a lower velocity than the ejecta, which is optically thick in early times. So very quickly, you're in a situation where you're just looking at the outer layers of the ejecta and not at material that's actually stripped from the companion. And so you have to wait till late times when the supernova has faded a lot to actually then be able to make the measurement that you would actually be able to see if that material exists. And this is why the near bright examples are so important here, because you have to wait until it's faded and you have to use big glass time to get high Sloan's noise data. So what do I do here? It's just a late time nebula-phase spectra. This giant line is just an iron line that's common in supernovae at these phases. And what you're looking for is a narrower bump on top of it at H alpha, because the velocity width of this material is expected to be like 1,000 kilometers per second, where the broad line is about 10,000 kilometers per second. And what you can see, you pass it, is that there's basically no narrow feature at this wavelength. And then if you go through simulations, models to basically change that flux into a mass limit, it's 2 orders of magnitude too low. So for this particular one, we can infer that there's not a companion there. Other people have played this game as well for a number of other supernovae. I think one of the best studies is done by my student, Michael Tucker, which I'll kind of go through. You can look for not just hydrogen or not just H alpha, but you can look through other lines as well. One of the challenges is that there are, of course, galaxies also have H alpha, except usually the good thing is that those are at a smaller feature than we're looking for. So you can separate them out by the width of the lines. Hundreds of kilometers per second, galaxy, thousands of kilometers per second, stripped material, 10,000 kilometers per second is the ejecta. But you can also look for helium as well. And we have not found any on the normal ones. And he's played this game with 111 nebular phase 1As that are in the literature. And these are the limits here that he can place. And you can see that all the limits are more strict than the typical models. Well, almost all the limits are more strict than typical models for main sequence subgiants in helium stars. So this would imply that the majority of 1As are not due to a nearby non-degenerate companion, because we don't see the hydrogen. In the less certain statement, we don't see the helium. There's other effects that you could expect as well. So one thing I should mention here too is that there are a number of weird supernovae that are starting to pop up and have for a while, but at very low numbers that do show hydrogen emissions. So it's not like this is a statement for all 1As. It's increasingly appearing that the population is probably diverse, where the majority are probably double degenerate, and that some might be single degenerate, but that's still an active area. Another way you can do this too is looking for other bright nearby examples. Is that the ejecta, when it strikes the companion, instead of just looking for that material 8 times, you can go very early and look for the direct interaction of the ejecta with the companion itself. Obviously, this depends on the viewing angle, depends on the size of the companion as well. But basically, the idea is that the ejecta comes out, strikes the companion, and a blue flux excess should be expected at early times. The best observed early supernova so far, the best light curve is ASAS-SN 18BT, which happened to go off in the Kepler K2 field, and then those pixels were downloaded by the KEGG survey. So here I show you the discovery image, the G band and the V band. This is when we were switching between G and V. Here's the Atlas light curve in O. Remember, that's a redder band, and you see the almost ridiculous Kepler light curve of this. This is actual light curve. This is not a model or anything. This is data points with error bars. If you look at the very early times, the supernovas kind of broke our general thoughts on early time 1As, because most 1As of the early time have been fit by a single power law pretty well. The earliest ones were like T squared, which is exactly what was kind of expected for a fireball. So basically just constant temperature photosphere expanding. That then went away, but most were still fit by a single power law. But it's quite clear that a single power law rise does not fit this data now. These large residuals. And then even double power law, there's still some residuals, although at this level, it's not clear if it's K2 systematics or the supernova. Because there's no wiggles here, I think this is probably actually real. So even double, a more complex power law, simple model doesn't fit either. So you might say, oh, I finally found this supernova was one of these blue excesses. A lot of people describe these as bumps, which actually I think is poor in the supernova field, because I think a bump as having going up, down, and then up again, where most of these, not all, are just kind of, I would say, 2-component, where they have 2 different rises. And if you fit the typical models for the expected interaction, they have large residuals. You can't actually do very well at all. And the fundamental problem is that all these models rise quickly very early on, and then they slow down before the radioactive decay takes over. So basically, it's injecting features early on doesn't really make look like the models, and that's kind of generic with these models because the ejecta strikes the companion. It's not hitting the companion, then it strikes the companion. It's very quick, and so they usually have these more abrupt rises than what we see here. Also, there's no hydrogen here, so it's probably, I think we can rule that possibility out. That's actually more exciting because now we can use these early time light curves to understand physics. We have a large sample from TESS now. This is just from the first 6 sectors, work done by Michael Fajna. This is another ASAS-SN supernova. I think it's still the brightest, or it's one of the brightest that was in TESS. Playing a similar game with a nearby companion to rule out large ones. We haven't had a particularly exquisitely nearby bright one that has happened in the TESS field of view yet, but should happen. These are by a postdoc and a grad student at OSU. And what's interesting with TESS is that this was just 6 sectors. There's of the 26 primary mission sectors, and it was almost a year in. So there's something like 35 or something sectors still. So a lot more supernova to go through for 1As. And also we can play a similar game with core collapse where you can constrain their radius just by looking at the early time light curve. And that's work that Patrick Vallely has just published. I'm sorry. Are there any questions on kind of supernovae and nearby bright ones with particularly good data? If not, I'm going to go on the.
So for the core collapse, it looks like the uncertainties are bigger. Are they just because they're intrinsically dimmer? Or what?
It's a great question. A couple of things. So if you do a volumetric survey, or sorry, if you do a magnitude limited transient survey, you will find like 80% or something 1As and 20% core collapse because the magnitude is just so different. So if you want to get roughly the same numbers, this is more sectors, but it's still not quite enough to make up for it. Yep. So so here it's kind of going further down in the barrel to get this number of core collapse.
Right.
Yeah, so just real quick, so for the companion impact result is very impressive, and I was just wondering if there is also any complementary method that you can determine that the majority of type 1As are double degenerate.
Great question. I have an entire colloquium on this that I still skim on. I think there's a number of convincing ways to look at this. I would say it's not completely accepted in the community, although I think it's becoming more accepted. One of the ones that always stuck out to me is just that there's not enough X-ray flux in elliptical galaxies to explain the accretion you need onto the white dwarf to explain the 1A rate in elliptical galaxies. So then you have to automatically invoke some heavily obscure, like a self-obscuring model to not have those X-rays. Basically, just dumping material onto a surface of white dwarf to build it up. You know the 1A rate, you know the IMF for white dwarfs, so you know the accretion rate onto white dwarfs that must be in elliptical galaxies if you want them to be single degenerate. It's just nowhere near enough. That's not true, obviously, in spiral galaxies because we have X-ray binaries, which then swamp the signal. What else is another way? I'm blanking on one that I like. Those are my 2 favorites. Anyway, there's a lot of different ones. I don't want to eat up too much of my time.
Sure, thank you.
But yeah, I'm happy to talk more afterwards. Like we could talk for hours on just the subject. That's kind of my favorite subject. All right, long baseline photometry, then I'll skip a couple. So as a result of as just hurrying for transient sky, for transient objects, you have to take many photos of the sky over and over and over again. That's pretty obvious. But this is then a very nice data set to find variable stars in. And that's what we've been doing in ASAS-SN, and other groups, including Atlas, has done that, has recently done that as well. Here, I'm showing you just the new variables discovered in ASAS-SN data with a machine learning typing that was done by Therendu, one of the grad students at OSU, on the left-hand side. And you can also then make this data public. I know some of you are familiar with the ASAS-SN Sky Patrol tools. since everything is done by tweet now, here's just a recent tweet by one of our members, where we now have over 1,100 different independent users from 500 cities around the world, including 65 countries. That's in just January 2021 alone. So that's not total. And I view this as very good in many ways. It gives our data out, gives us citations, et cetera, et cetera. Actually, I view this as kind of like an equalizer for astronomers across the globe, kind of equalizing across the access to telescopes, which I'm particularly fortunate being in Hawaii to have lots of. And then you can just look at the citations. This is not the ASAS-SN paper, this is just the citations to the Sky Patrol. And you can see that there's a lot of demand in the community. Here I want to attempt my first ever live demo. So the problem with the Sky Patrol is, if you want to get a light curve of a single source, I don't do any selection for you. This is the website for the normal Sky Patrol. You either enter a source and resolve the name. Here I've just pre-entered an object that's in the LMC. That's a Thorne-Zipkoff object candidate because it has a crazy light curve. And then when you click go, it takes 10 minutes per light curve because I have no selection for you beforehand. And if we waited 10 minutes, we would end up at this page, and then you can actually send this link to anyone you want, so it doesn't have to rerun it over and over again on the same source. But you can see that the Thorne-Zipkoff objects have crazy light curves, going over 4 magnitudes. So that's quite a useful tool because we have no selection. You can do whatever you want. It's just forced aperture photometry on our individual images. Problem is it takes a long time. So we have 2 other resources that are already available. One's our variable star database that Therendu's gone through and found all those variable stars, all of their light curves were then made public here. And we also have a photometric database, a photometry database, where we have a bunch of pre-computed V-band images already for you to go. So you can just enter RA deck and on some reasonable radius and go, and it'll pop up if there's something there. I don't know why it's going particularly slow now. There it goes. So no sources are there, so I have to increase it. Okay, so there's a pre-computed V-band, so then you can get a larger number, but at the max is about 1,000 sources, just because of all the machinery behind. It's not fine-tuned for huge amounts of data. The zoom button is in the way. It's funny. Okay. Sorry. Hi there. And if you click on a variable star, of course, we give you the face folded and what we think it is, et cetera, the type of the variable. The new tool that we're just starting to use now is here, which is Sky Patrol version 2. This is hosted at University of Hawaii. I worked with a CS grad student here to develop this. Here we have pre-computed light curves for over 100 million sources, stars, asteroids, comets, blazars, AGN, galaxies, et cetera, all cross-matched. You can do huge searches quite quickly. So if you want to do this now, rather than 6 arc minutes, this is 6 degrees on the sky, and you want to search. Kyle has spent a lot of time making this cone search extremely fast. I haven't seen a cone search anywhere near this fast anywhere else in astronomy. 500,000 sources are returned just because I had this huge cone search in, I don't know, maybe like 10 seconds or something. You can ask for random light curves if you want. If you want 100, good enough. You can get 100 light curves. Each one you can click on. There's 80 QL, so you can go between all the different. We have Gaia database, we have tick IDs, we have a huge number of different tables that you can actually do 80 QL queries on. On the website, there's a slightly easier function if you don't want to think about the 80 queries. You can just go to like tick. I can come over here and I can find almost 10,000 sources. Enter, these are the tick IDs of ASAS-SN variables, just to make it more complex. And then I can search. This will take probably about 30 seconds to search, or a little less. Oh, I just did 1,000. Okay, so it's super fast. Anyway, 700. The button isn't here yet, but you'll be able to click and say, oh, give me those ones. And from the website, you'll be able to download about 10,000 light curves in about a minute. And then maybe more impressive, so you can also look at a particular variable if you want. And then what's maybe more capable tool is actually the ADI to actually do this, where you can go through and import our ASAS-SN client. And you can do many things. There's you can see all the different tables that we have in from all the different sources, including multi-wavelength. And you can go down, you can get random light curves similar to what I just showed you. You can do joins, whatever you want. You can find an individual star, take a periodogram in the API, or you can build your own, of course, and then you can immediately plot and find this variable. So then those are all the tools that we're trying to make this useful to the community. In addition, we have a citizen science project that we're doing where we're basically putting ASAS-SN light curves, V-band light curves there to be identified by the community. As of a couple of days ago, we already had almost 250,000 sources classified by almost 1,000 volunteers. And this is all work that's been done by and led by Theron Du. So if there's any other questions on that, I'm going to skip a bunch and go to challenges, if not. So the challenges are kind of similar to what, the similar causes to what's giving us opportunities is our data rate is rapidly increasing quite quickly. And so it's going to become more and more challenging to sift the wheat from the chaff. Or another way of thinking about it is actually to make full use of the data we're already collecting. And almost certainly we're just not going to be able to make full use. So here I showed you the black line in the beginning of my talk to motivate the interest in kind of transients in the direction we're going. But the red line is what we've actually classified all the way through 2019. And you can see that they're just not keeping track at all. So we're discovering all these new transients. And then basically we're doing mostly nothing with them. It's a little bit, not completely true, but basically nothing with the majority of those transients. If you want to break down who's doing the classifications, this is from 2020 now, is that ZTF, using mostly 3 different telescopes, is doing the lion's share, followed by ePesto, which is a European collaboration between a number of different institutions. SCAT is a pilot survey that me and my grad students have started running on the 88-inch. Which is a phenomenal telescope, and I'll tell you in a second. And here on the left-hand side, I'll just show you the 60-inch Palomar, which is the currently has SED machine and is the #1 classifier for transients. But the way we're currently doing this, so SED machine is fully robotic and has a SNFs-like spectrograph on it. SNFs is an older spectrograph and a small field IFU on the 88-inch. I was recently awarded an MRI to roboticize the telescope, so $1 million to do so. We're changing the telescope control infrastructure. We're improving the dome, the RA and deck drives. Right now, we just went through our critical design review for a tertiary that can switch between all the instruments in real time. We're building Kyle's building a scheduler. So the whole thing would be fully robotic, which then enables us to get a small amount of time every night, which is currently very difficult to do in any classically scheduled telescope, which is basically how we're doing this. So if once it's fully roboticized and become more efficient that way, and we get about 1/3 of the time on the telescope, which is feasible, but not guaranteed by any means, because it's used by the whole UH community, then we can start to get to something like this, where we're basically classifying 3 to 4 transients every single night. The advantages of the 88-inch over the 60-inch on Palomar is on a better site, has higher throughput, better scene, slightly better instrument, although higher resolution. So SED machine can get away a little bit of less exposure time because of that. But overall, it's just the bigger telescope, much more efficient. And then we're trying to get off the ground a robotic classification of astrophysical transients, where we'll go from transient discovery to triggering spectroscopic follow-up to classification to publication of that classification with no humans in that step, at least a preliminary classification. So I think this is where we have to go. to make better use of the surveys we currently have. And it's not an and or, it's not an or, it's an and. So it's not like this will replace other efforts. I think we just need to ramp up all of our efforts and make them as efficient as possible. And the real problem is that LSST is on the horizon. And this photo, literally, if you zoom in, LSST is not that far away now. I know it's, for some of us, it's seemed like that for a long time, but the floodgates were really just completely open with LSST, where we won't be able to keep up. And there's no hope of doing spectroscopic classification for even 1% of the transients that LSST will discover. So we need to start doing now, and many people are, start to build the groundwork, build training sets of brighter transients for the surveys we have that are spectroscopically classified, and then figure out and develop methods, whether it be machine learning or more classical, to identify interesting transients out of the LSST stream. And that's work that just basically has to start now. And with that, I'll just ask if there's any questions. These are the things that I'm interested in, so.
No, do you mean the questions on this RoboCat part or other part?
Any part you guys want. I'm happy to chat about anything.
Do you have more slides to show?
I can go back and I could talk about 14KO if you guys would want. I know there's probably interest here for that.
Oh, I mean, I do have a question about the classification. I mean, you mentioned I mean, spectroscopic classification. So have you thought about the prospects of using multi-object spectroscopy surveys to, significantly kind of think about that possibility and use those surveys, try to accommodate some of the needs for transient follow-up?
Yeah, that's a great point. So I think it's like SDSS-5, which I think is what you're thinking about, and also DESI, where they have robo positioners, could play a role here. It's a little challenging though, because it's a slightly complex problem, especially for Sloan, where the depth Sloan can get to in the exposure times they want, there won't be multiple transients of interest in a given SDSS pointing at a time. That's not that big of a problem because you would still go, but then what you're doing is you're dictating the survey strategy about which field you go to based on the transient science, which isn't a problem. Like, that's more of a political question inside SDSS. If you go to DESI, it's a little bit better because you go deeper. So then when LSST is going, then maybe you can get some of these samples that way. But it's just this entertaining problem that to go to the depth that you need for the spectroscopic surveys to have many targets in a given field, the transients are then so faint that you can't actually classify that many without using large glass time anyway, and the spectrum will be kind of crummy. So it just happens to be that the density of at least supernovae on the sky is low enough that it's basically like a one-off anyway. And so you can combine this with other surveys, which is a thing that people are thinking about. I think you know that as well, of course. But it's challenging because then a supernova doesn't want to, if for a nearby supernova, if you wait around for a week or two, it's not particularly useful anyway to then classify it. So it just is weird. Yeah, I put a lot of thought into this, and it's just one of those problems where it doesn't seem to converge on itself. But I'm happy to be proven wrong if somebody has a better idea.
Well, we can build a 10 meter.
Yeah, well, yeah, so you're actually, there's an CFHT here in Hawaii, putting on my Hawaii hat now, wants to build what is it called? The Mauna Kea Spectroscopic Explorer, MSE.
Mm-hmm.
So there you replace CFHT. The dome is just only slightly bigger. The ground footprint's exactly the same, which helps with political problems. And you could build a 10 meter that's multi-object. So it is something that a lot of folks are thinking about doing. So then you can get a higher number. And of course, Mauna Kea is pretty far south. So then you can reach a lot of what LSST will be discovering. Although the timescales are a little bit, LSST has to stick around a long time. That take a long time to build.
Thank you, Ben. I see there's hands up, so let me open the floor to people. So Brian, you want to ask a question?
Yeah, sure, Ben. Thanks for your talk, and it's great stuff. So today is the anniversary of 1987A, Supernova 1987A. So in honor of it, of course, I have to ask. Someday the great day will come when we have another galactic or maybe M31 supernova where you see the neutrinos first, as we did with 1987A, and now there's this early warning system. So what are these, what does that mean for these surveys? You guys have a protocol for that?
There's a lot of interest in ASAS-SN, so it's very easy for us to manually go in and switch. I should actually just build it in. So one thing I didn't mention is our multi-messenger work with LIGO and with IceCube, where we've successfully gone from a neutrino hitting the ice in Antarctica to our unit in Texas being open shutter on source in something like 37 seconds.
Oh, that's
and we have a wide field of view too. And so of course, if you have a galactic supernova, then it'll be relatively well localized, probably by things like, actually the super coming, if it's galactic, I think super K might be blinded. It might be too bright. I forget. I thought there was some saturation problem. But anyway, presumably we get a good localization. So we have, within a couple degrees is fine for ASAS-SN, where each point is 9 degrees across. But we don't have that built in right now. I should actually start to think more about this again, to actually build in those triggers. Seems like I just want the neutrino community. It's not a big deal for this to give us false positives as long as it's not every night. So I don't care if you give me a false positive once a month, right? It doesn't use much of our time. So that's a good point. I actually write it down so I remember this.
Yeah, very good. Thanks.
Thank you.
Gautam? Gautam, you can
sorry, just unmuting myself. So on the subject of RoboCat and automatic classification of these sources, what are you actually going to be using for photometric classification? Can you get away without spectroscopy for the most part?
So the way I view RoboCat's role is to basically drastically increase the size. The one thing I didn't show you here is that in 5 years, well, now it's probably 5 years, it was 4 years. But in 5 years, we can basically double the number of transients mankind has ever classified spectroscopically. So I view RoboCat's role as kind of continuing to build that training set with more uniform data, because then we don't have to go back like decades in data and then actually go between surveys. So then we can basically build that classification data set.
But isn't the redshift range that you're going to be getting just a very different match to something like LSST? If you're being fed transients from something like LSST, you're never going to go as deep, right? So
yeah, you have to build into obviously the classifiers, basically some prior on redshift, and then build in K corrections to actually shift the spectrum that we get in the optical to other wavelengths. Mm-hmm. It's clearly the one good thing with sniffs on this point is that it's very blue. So it goes to the atmospheric cutoff. So then you get substantially more blue so that you can still use those spectra.
Yeah, it's just it seems almost a little circular because, with LSST, if you have to find a source photometrically, you don't know what it is, you don't know what its SED is. So how do you go about calculating a K collection using what model? So it'll be an interesting next few years, I think.
Yeah, I mean, how to say this? There are many problems that I know are hard, but there's going to be a solution for them. There are other problems that are very hard, and you're not confident there will be a good solution. I think the LSST photometric classification of the majority of the transients it discovers is in the second category, in my opinion, on that. It's not completely clear. For a large fraction of the transient, for a huge number of transients, we will, because they'll be bright, we'll have enough information, that's fine. But for the majority, which will all be near the detection limit of LSST, that is less clear to me. This is not a statement that LSST will not do great science. I'm super excited it's going to do great science. But that particular problem does seem difficult. And if this approach doesn't work, then I don't know what will.
So Shing, you can go with the next question.
Yeah, thank you. So thank you for this very illuminating talk. And I was just wondering, perhaps this doesn't really have an answer, but how do you actually determine or prioritize your spectroscopic follow-up resources when you are really, bombarded with all of these discoveries? Do you have a way to sort of quantify the science return, write down in some way to quantify this, or do it obviously depends on your science goal, but how do you actually prioritize?
That's a great question. You literally just struck at my past 2 or 3 group meetings. We've been having arguments back and forth about this. Is what are your goals and how do you prioritize? So right now, SCAT isn't particularly large, and it does take a lot of people time to go in. So we prioritize things that we might be interested in. So the first cut is magnitude, and then we also look at like nuclear transients specifically because I like them. I like AGN, I like TDEs, etc. So there's some combination of those 2 cuts that are going into our current classification efforts. If we went to something like RoboCat, I think it would quickly become critical to erase as many science-driven pressures as possible, and just openly just make a magnitude cut and say we're going to classify everything that we can down to a certain magnitude. The reason I think that's important is because then you know what you selected. So then when you're actually trying to build classifiers on that data set, it's as minimally biased as possible. So another way to look at this, if I just feed everything, if I feed a classifier only nuclear transient spectra, then I'm gonna have a very different classifier than if I feed it something where I know the selection effect. Of course, there's still selection effects in there, but I think the idea, if you wanted to go something like RoboCat, you would want to try to minimize all the selection effects that you could, knowing full well that there's probably more effective ways to get more science per telescope time out, ignoring the classifier effort, the portion. That's a great question. I think there's no right answer here, but I think it's just debated. It's going to be debated back and forth.
Yeah, great. Thank you.
Okay, so let's have the last question from Paul.
Hi, Ben. Thanks for a great talk. So far, people have mostly asked about spectroscopy in terms of classification and triggers from LSST, but I wonder if you could comment on gravitational wave triggers and in particular spectroscopy of neutron star mergers. Are you in a situation where you could say something useful about element production in those events?
That's a great question. So the only spectra of a kilonova that have been published in the first 24 hours are my own. I didn't talk about that at all here. So obviously I'm very interested in this question too. I think there's 2 ways to think about this problem. One, I think it's become clear from the last LIGO run that we were just exceptionally lucky with the first kilonova. Basically, it just happened to be nearby and bright and easy compared to other ones. That's still a statistical statement, so it's not completely guaranteed that that's true, but the rates are kind of pushing in that direction. Fine. And so then the question is there's 2 parts. One, you define the kilonova. So the problem with pushing out in redshift is it becomes hard as a strong function of the distance you're looking away, not just because things become fainter, which is once your sky limited right is hard squared, but it's also hard squared because the hard cube because the volume is getting substantially larger as you go out. So then there's going to be more interloper transients that are in the right redshift range within an error. There's also a couple of factors, I forget what exactly they are, from LIGO itself, because as you go farther away, then the uncertainties on the loudness becomes less, of course, linear with distance, but then that affects things like localization, both in redshift and in RA index, which then increases the size of the error box you're searching on too, even though now the volume is even larger already. So all of these things stack up to mean it's very difficult, and we're going to be in a situation where we'll get real kilonova alerts from LIGO, and then there's going to be this similar to what happened before. There's this huge effort to then go find the counterpart, but there's going to be not just one new transient in that's consistent with the error box. There's going to be lots. So then we already seen this where you're going to have to then go between surveys and say, oh no, but I saw that 2 hours ago, just below my threshold. That's not fast, or maybe not 2 hours ago. It was 2 hours before the alert or something, right? My point is so that it couldn't be the kilonova, so you can roll it out, but you're still going to be left with a selection of transients that are going to quickly need to be spectroscopically classified if you want to know which one of those is the kilonova quickly. And the reason you want to know it's quickly is because the early time light curve and spectra are going to be interesting. You want to make sure you get the peak and the decay. The early time spectra, at least in the first one, not particularly interesting in the first day. Maybe that's good, maybe it's not. It's mostly just blue. There's not very many lines that early, but you really want to make sure you get peak brightness so you can at least compute bolometric light curves of the kilonovae so that you can do element production calculations. And that will require, I think the first one peaked in, was it like 20 something hours or something? So you don't have much time to do this. So you're going to need to get on, you have to go from LIGO to transient surveys that are deep enough. So SAS-SN can cover the whole area quite quickly, but maybe we're not deep enough for the majority of these sources. So we're just kind of checking, and we did that already. We can do that very quickly because we're large field of view. But the deeper, slower surveys will often have to go through, find these candidates, put them out quite quickly. We're starting to get that was starting to work well, but then we're gonna have to go through and spectroscopically classify these. And I would argue you don't want to use all of the Gemini time for the United States to do that. So then you're going to need quick, efficient, medium aperture telescopes to go through and vet those sources. And then once, of course, you have those sources, if you find one fine, then everybody is going, whoever's a spectrograph is going to point at the first few. That's great. We're going to get data that way. And then as they become a little bit more boring, then we'll get to the situation where it goes back to the medium aperture telescopes to get you more data than the larger aperture telescopes are willing to give you the time for. It was a very long-winded to answer your question, but I think I covered it.
That's great.
I think I covered it.
That's great. Thanks.
All right, excellent. So we're past the hour. So let's give Ben a round of virtual applause for a great talk. Thank you, Ben.
Thank you all so much.
Okay, so just to confirm with you that we're gonna, let me stop the recording.